If we have a Defense Department that is unable to have an operational capability because the lack of a component, I mean, that is a huge crippling factor for the United States.
Being able to pull that left, right, pull that into the digital twin realm yields really high ROIs. We're seeing 20, 30x ROI.
This is huge. This is a joint service program, right? So it has a JPO, variables across the board. And lo and behold, now you've been able to not only iron out a lot of these, kinks and concerns, but provide a capability. So what's next for Nimbus? It seems like the paradigm shift in the government is now is saying, look, microelectronics enables things. Schoeller, I'd like to thank you for joining us here on Micro Journeys. Really appreciate capturing such a busy time here at GOMAC, and your willingness to talk about not only the influence that you've had to the industry, the way that Nimbus Services is going in and changing and kind of challenging a lot of the thought process of the way people had been doing a variety of different electronic enhancements, analysis, and a spectrum of different things that has been extremely impactful to current defense programs and the future of not only defense acquisition, but defense sustainment. So thanks a bunch for joining.
Well, thank you for having me. It's a lot of fun to be here. And I know you're just getting this podcast off the ground, so I'm very honored to be one of your first guests.
Well, and I don't want to make the snafu that some people will make, and want to make sure that the listeners get this right. It is Schoeller Porter, correct?
Schoeller, yes. That's how my family's been pronouncing it for millennia. So.
Excellent. Well, thanks for joining. And, we were getting started here and kind of talking a little bit about, kind of your heritage, your background, and your education, right? So one of the things we started out with was like where you went to school. But before we get to that, what really got you involved or interested in, technology as a whole? Were you always interested in this? Is it something that, is more of kind of a family push? Like, how did that all?
Oh, no. This is all my I'm the only person in my at least immediate family that's involved in technology in any way. My father's a pastor. My mother's a teacher. My brother works in manufacturing. So I was always kind of a little bit of an odd kid, with my head in the books, trying to tear things apart. Eventually, I looked up in the sky, saw airplanes, thought those were really neat. And that bug never really got shaken off of me. And so I went to school to be an aerospace engineer at the University of Illinois. There I got involved in computers and kind of that side of technology. Worked at the National Center for Supercomputing Applications.
That's right around the corner, right?
It's part of the University of Illinois, yeah. From there, went to Wolfram, then did my own things for a little while, and then Nimbus. So it's been an interesting and circuitous path in the sense that I left school when I graduated from college. I got out with an aerospace engineering degree, then went straight into software engineering.
How was that dynamic? I mean, that's not necessarily a direct overlap, right?
It's not. Well, it was adjacent for me because I went to Wolfram, and Wolfram is, a technical computing that's, the mathematical engine, can solve basically any mathematics problem symbolically, which is its unique capability and I guess skill and why it's used heavily in science, math, and technology. And so I wasn't too far away at that point from kind of core engineering knowledge, and I found I was able to use the things I had learned there, particularly the math skills I'd learned there, to understand what customers needed and kind of what the product needed to do to be successful. But no, it wasn't directly in the field of aerospace. And even beyond that, a lot of what I was starting to do once I left Wolfram and spun out on my own, did some startup kind of work. It was all in the kind of big data analysis world. Some work in AI before we called it AI. Still called it machine learning and things of that nature.
It's interesting. You go online and you see, when AI was kind of getting its grassroots, right? I mean, you see some of these images of people putting, video footage up of, I think one of the big ones is there's a number of different actors that are trying to, eat an ice cream cone or comb their hair or something like that. And and you see like body parts just randomly move all over the place where maybe there's a third arm that comes out or the eye just kind of sinks all the way down and the such. So it's interesting because there's a vision associated with this, right? And it goes back to just engineering principles, right? problem sets. Like, I mean, as an engineer, you're given a problem every single day. I mean, in your situation, almost every single hour. And they come in so many different directions. You're having to just solve them as they come in with the tools that you have, right? So, it's interesting because having your education background and then going into your first career opportunity, not a direct link, but the commonality is the problem solving, right?
Yeah, and that's what I found with engineering is that it gave me the set of skills to be able to solve a broad range of problems,
Yeah.
Irrespective of what the domain is.
Yeah.
I mean, obviously, I was trained in aerospace, but these days I solve business problems, right? While I was at Wolfram, I also went back to school and got my MBA.
Okay.
And so I found that interesting, largely because business problems tend to be unconstrained, right? Engineering, you have boundary conditions. You're trying to solve for optimize for some particular solution or particular domain of the problem you're trying to solve for, right? Business, you don't really have those kinds of constraints, right? You are the one who defines what your market looks like. You're the one who defines kind of what your strategy and goals are. And so it's similar in some ways in how you want to solve those problems and the skills you need to have in order to apply to solve those problems.
Yeah, I remember in calculus, I mean, they didn't really go over TAM, SAM, SOM, EBITDA, OPEX, CAPEX. I mean, these are all things that if you want to migrate out of, pure engineering, but be somewhat of a leader in the engineering space, these are terms that you need to know, and you need to know them pretty well, or else no matter how successful your technology could be, if you don't have an ability to integrate these things in, I mean, it's going to fall apart.
Yeah, and that's the exact reason I went back and got my MBA. I started at Wolfram as an engineer, working on the mathematical kernel, the piece that does the actual math. I was the engineer that supported and ported the mathematical kernel to all the different Unix platforms. So at some point I was supporting 14 different variations of the mathematical kernel on all these, Solaris, both 32-bit and 64-bit, SGI, IRIX, the whole litany of them that existed in the early 2000s, most of which don't really exist anymore. But so I was the technical guy on these calls with Sun and SGI and DEC, HP, all the big companies that made these computers. Their business people are on the call, and they were kind of yammering away in some language that sounded a lot like English, that used words like EBITDA and so forth, that I had no idea what they meant. I mean, I understood them individually as words, but didn't understand necessarily how they strung together to mean something meaningful. And so I figured if I was going to go anywhere in this world, I had to learn that language.
A smart move. I mean, because if your experience was anything like mine, which it sounds like it is, one day you're engineering, the next day you're talking financial terms, and it's the deep end you're thrown into, and it's a very short window of ability because people will read through your lack of understanding on these things pretty quickly. And so having that MBA kind of background, it should be something that is integrated into a lot of engineering, curriculum as part of the, general education, because it's a tough thing to take on. So
it is, yeah. And right after I got my MBA degree, I was by that point Wolfram Alpha had started. If you're familiar with that, and so I was took on responsibility for the launch, for the infrastructure behind the launch of Wolfram Alpha, all the computers to be able to, again, it's math heavy, so a lot of computation necessary, a lot of computing power necessary, and then also the Wolfram Alpha app. So I really was kind of thrown into the wolves to figure out, well, how do we have a successful launch so that, people who are coming to this brand new Wolfram Alpha website to do all these exciting math problems and kind of dig through the data sets that we had and understand kind of the trends in those data sets and how they apply to them, to make sure it all worked, that the service didn't crash, that people could get the answers they're looking for, all those kind of things. And then with the app, how do we drive kind of volume through, again, cell phones were pretty new, smartphones were pretty new at that point. And the idea of having kind of this app version of Wolfram Alpha is pretty new. So how do we kind of drive and grow business through that different channels?
Yeah, I think I read an article one time that was saying that, if an app crashes, the likelihood of someone using that again goes down by like 95% or something substantial. It's and you're doing this simultaneously, right? So you have two different deliverables that are coming out. One that is, continuing to push the way on the computer side, but then you have this other piece that's a software app with a relatively new platform in cell phones. So now you're battling two fronts, right? You have new app that can't crash, that can't have problems, can't have bugs on a system that really isn't defined as its reliability for not crashing and not having problems and the such. So, I mean, talk a little bit about what that experience was like. The app one is actually really interesting because I think that kind of scopes out a lot of the stuff that we'll talk about with Nimbus here in a little bit.
A lot of the understanding kind of what was needed for the Wolfram Alpha app was really trying to define how one uses a highly technical service like Wolfram Alpha on a constrained environment like a phone, right? How do you enter equations? How does it give you the responses back in a way that you can see and read? And again, today's smartphones are really big, right? They're the size of computer screens, resolution of computer
mine even
screens.
folds out like
Some of them fold out.
Yeah, like a tablet.
But at the time, this was the days of iPhone 4 had just come out, maybe, right? So screen sizes were a lot smaller. The device sizes were all a lot smaller back then.
And the compute power is a lot
Compute
smaller.
power was a lot lower. The network speeds were a lot lower and a lot less reliable. So yeah, it was a lot about how does one even interact with the app in order to really communicate with it, right? How do you enter? We call them queries. Enter a query, and find out how far away is the moon right now? And kind of what information do you get back that makes sense and is useful for you when you're out walking around with your phone versus when you're sitting at a computer. So there's a lot of that. Some of it's UI based, but some of it's just what does the experience and interaction really need to look like to be successful, and how do you deal with the cellular network not working in this particular place, but now working again, right? And so the experience is good, so they come back and keep using the app and gaining knowledge. That was kind of the whole intent.
Yeah, and the interesting piece that you said UI with the user interface. I mean, that's a area in which there's not a lot of data. I mean, at this time on user interface. Now, I mean, the people pump out apps for a variety of different things. There's just a lot more collective, learning that people have done in developing these different types of things. So, I mean, here's an initial instance that you're at where unknown area, I mean, more or less, and in that scenario, you're helping to kind of challenge the industry in an area that people today are using on a common basis. So, as you're navigating past your time here, do you take any other kind of career pit stops before you get to Nimbus Services, or is it a pretty direct?
No, I spent some time doing my own consulting work and working in startups. And sometimes as a consultant, sometimes directly for the startup, none of which you would have heard of because none of them succeeded.
Yeah.
Turns out, failing is a great way to learn. But through that experience, I got exposure to a number of different kinds of businesses. I worked as a consultant for TrueCar for a number of years.
Oh,
for
interesting.
Example, yeah. Did some small jobs for like the Advocate for a little while as well.
TrueCar, that one. I'm sorry, I'm going to pull us back on that one a little bit. Time frame wise, I mean, was this kind of in the early onset where people were, purchasing cars online?
Yeah.
Okay, so once again, yet a set of user interfaces challenging a dynamic of people not going to the big car lots and the such. And
Yeah.
I mean, how did that experience shake out? I mean, what was it like for you there?
Yeah, so I was working on more the back end sorts of things and the front end sorts of things, and looking at they have massive amounts of data that come in from all the dealers about what cars are being sold at what price. The whole goal of TrueCar is to figure out a reasonable price, not necessarily the cheapest price, right, but a good solid price for a car that's fair for everybody involved. And so that is obviously a big math problem, right, a big data crunching problem. And this is when I was working a lot on big data. So I was working with their team to implement a system in Hadoop that would allow them to do that.
So yeah, I'm assuming it's something where, I mean, and this is a simplistic version, but you have your Kelley Blue Book number. You have a number of which you were able to find data on the highest price point sold, and now you have your bookends. And then that's a way for someone to go in and say, okay, I'm willing to pay X amount. You look and see if it's within the bookends, and now you see the profit margin, and then all of a sudden you say, okay, car can be sold. I'm assuming that's kind of a simplistic way.
I think that's a simplistic way to think about it. I can't really disclose kind of what the algorithm looks like, and I don't know if I knew all the details anyway. Just focused mostly on the mechanics of making the algorithm work within kind of this new platform at the time, again, Hadoop, that would allow them to compute, use larger volumes of data, get more intelligence, more insight into what the right pricing should be for a car. Again, what a good sales price for a car ought to be a fair price for both the consumer and the dealer. Really interesting. And one of the things that you also find out of that is that most data is terrible.
Oh, yeah. Garbage in, garbage out, right? That's the buzzword.
A not small amount of that was also how do you clean that data and then turn the data into something that can be computed on in a way that's meaningful and reasonable and doesn't have a lot of error.
Is it safe to say that this is kind of the early onsets of machine learning that is being applied into this?
Machine learning was kind of in its infancy around that time.
Okay. So very interesting. And you were describing, before we took the detour here, no pun intended, on the TrueCar, that there was a couple startups that you were working on. You had consulted for a little bit. Anything else within that journey here that you took on?
A lot of it was focused on these ideas around data analysis and how can we apply machine learning techniques to that data to extract useful information and to kind of predict what the next thing to do is. Okay. So one of the things I was doing at that time was looking for call fraud with a voice over IP company in Chicago.
Oh, okay, interesting. And as you're progressing through this, now you start taking on a role at Nimbus.
Yeah, right around the time when I was working for the voice over IP company, Bob Graybill, the CEO of Nimbus, gave me a call and said I've known him for years. When I was working for Wolfram, I'd go to supercomputing conference every year, and I met Bob there when he was working with the Council on Competitiveness, and so we kind of kept in touch loosely over the years, and so he knew what I was up to, and he gave me a call, and we started working on something that became the trusted data repository activity we were doing.
And that's where I first heard about Nimbus. I'm trying to rack my brain here, and I know I was at an airport, and I was on a call, I think it was with DARPA at the time, and someone was asking me about, have I heard of any cloud services for microelectronics? And I said, I said, not really. I says, what are you thinking? They said, well, we got, some contact, probably a business card or something like that, from a Nimbus Services. And I says, I have no idea what this is. And then the description came over and I was like, So, well, this is interesting. Now, I'm willing to bet that I was probably in Chicago. And I only say that because I fly United. So the likelihood is it's either Chicago or Denver, one of the two.
High degree of likelihood you're in.
So anyway, so you were contacted and asked to join over at Nimbus. And at the time, how big was Nimbus? I mean,
I think I was the 18th employee, 18th or 19th employee.
Okay. Relative to where it's at now,
we're 35 now.
Okay. So there's a growth trajectory that's about to happen here. Okay. So you get contacted and you're asked to go ahead and take a role on here, and you have this trusted repository capability. So you were saying.
Yeah. So when I joined, the Trusted Silicon Stratus existed. So the cloud service pieces had existed, and through what was the Trusted Tools and Techniques program, T3, we had validated that you could use engineering design tools, EDA tools, in the cloud to do designs, and it was a reasonable thing to do. Again, so this was 2018 when I joined. Before that, whether or not one could reliably use engineering tools in the cloud was still something of an open question, and persisted to be within the DoD for quite a while afterwards.
Because historically,
it's very common now, right? But
historically, it was more of a data repository, not so much a enabling function for extension of tool sets. Correct?
What's it? Trusted Stratus?
No. I'm just saying the cloud.
Oh, the cloud. Yeah. I mean, so get into a little prehistory of Nimbus. Nimbus is largely a contemporary with the cloud, right? We started in 2008. The Amazon Web Services started, I think, the year before, something along those lines, maybe 2006. We started running on our own infrastructure, but quickly moved to AWS like everyone else. And, we were one of the first people pushing this idea of doing engineering, interactive use of engineering tools in the cloud, right? So having a virtual desktop remote displayed over the web, right?
Interesting.
And this was all the way back in, say, 2012.
And it's common now.
It's very common
Yeah.
now. Yeah, it's very common now. So we were pushing that boundary back then, and by the time I arrived, it advanced to the point that that was pretty well sorted out. We had a cloud-based system where you could load engineering tools, load EDA tools. You could do full designs in the cloud, right? Highly reliable. Not everybody believed us, mind you, but it all worked. And then,
well, with any new technology, right?
Right.
There's always a question of concern. How much do I really want to invest my time, my money into something like this? Because if this proof of concept doesn't shake out, then I wasted a lot of, not only financial capital, but political capital in backing this kind of stuff.
that's right.
Yeah.
And then, what do you do with engineering tools? Well, you create data, right? You create designs. Those designs are data. And now, my role coming in was to figure out, well, what do we do with it? Again, I'm working in big data and kind of machine learning techniques at this time, right? So what do you do with that data? How do you maintain provenance and traceability of the data, which is very important within the DoD? Make sure, who changed what file, when, where, why, what touched what, as data moves from one system to another, right? How do we understand that the data on this side is the same as the data on this side? Hasn't been manipulated in any way. Not just for nefarious reasons, but also just bit flips, right? You want to make sure the data is consistent and correct, and you have reliable, right, communication between different machines.
Because it doesn't matter. If it fails, it fails.
That's
Malicious, reliability,
That's correct.
act of God, you had a failure, and that's not what your intended, end deliverable was, right?
Correct. And so that's what the Trusted Data Repository program was about, is how do we build that data system within Trusted Stratus to be able to support engineering data at scale for DoD needs, both for immediate use as you're working as a designer, chip designer, doing your chip design, and also for archival purposes. So you can go back and retrieve the data in the future, look at it again if there's a problem found, or if you want to respin the chip, or you want to, whatever it is you want to do.
As you continue progressing within Nimbus Services, there's been a number of different, what I would call milestones within the company. Maybe you want to touch on a couple more of those, because where we're at today is extremely exciting. So
Sure. Yeah, I think two big milestones to think about, kind of the next major milestones after the Trusted Data Repository. One, the Advanced Technology Center activity, ATC. That was really interesting. Is I think probably the first time that the defense industrial base primes, multiple defense industrial base primes, had gotten together to work on a single chip. So to kind of the idea was to take the best of breed technology from Raytheon, from Northrop, from Boeing, and from IBM, and kind of put them together into a series. There are 3 reference designs that were done as part of that, all integrated by MIT Lincoln Lab.
I'm smiling because getting all of the primes to play together, I mean, in and of itself is a monumental feat. And that right there, on top of the fact that you're asking them to share information, is yet another monumental feat. So very interesting. I mean, I have to assume that there was a lot of, I don't want to say it's horse trading, but there's got to be a lot of back and forth on what is the goal and what is achievable.
Well, I think we understood the goal pretty well at the time, right? How we get there was a bigger question, right? And you're absolutely correct. At that first meeting, it was, I'll never forget, a big table at one of IBM's facility downtown DC. Everyone just sitting there, arms crossed, right?
Probably with the thought, why are we here? This is never going to work.
Why are we here? This is never going to work. Yeah. So that first meeting was, I think, a little rough. But over time, everyone got to know each other, started to trust each other, understood we were all working toward the same common goal. Nobody was trying to steal anything from each other. We're trying to do something better for the common good, for the DoD. Right? Demonstrate that yes, we can have competitors work together on a single design. They can all have their own IP isolated away from each other. We can compartmentalize it and then assemble it into a chip that has the best of breed from everyone. And we were able to demonstrate that. And that program really demonstrated to the DoD that the secure design concept, or secure collaborative design concept, was viable, and was what led to the RAMP program.
Interesting. Maybe give a little description of what you mean by the RAMP program, explanation of where that is, and then kind of how you said it was an influencer into that.
Yeah, so RAMP was the Rapid Assured Microelectronics Prototypes. I think I got that right. So the intent was to build a cloud platform for the defense industrial base to be able to use to do designs for programs of record as more of an enterprise level capability that had all the security, compliance, and and access to tools, data, IP, and flows that would be necessary to support DoD and programs needs.
Okay, so this is a huge milestone, and at this time there was a paradigm shift within the Pentagon, pretty substantially. And what I mean by that is that the RAMP program was one of the pillars of microelectronics that was invested in, where historically microelectronics was mostly a commodity kind of purchase, and now there's a lot more investment, not just directly coming out of DMEA or DARPA or the service labs. OSD is playing a big role. So RAMP-C, SHIP, all flagship programs that are coming out of OSD, and having the ability to be the spark to the fuse that kind of lights this ramp piece is an interesting, item. And we've seen a lot of big benefits that have came out of, this framework of programs. One of which is some of the relationships that have come out of Intel, right? Some of the relationships or byproducts that are coming out in advanced packaging. But ramp is kind of the initial piece. That's the feeder into all of the other portions. And if that fails, all these other visions and concepts, don't have the wild successes that they've been having. So you helped to, spark the RAMP program. There was another set of, like you said, milestones that.
Yeah. So again, back in that 2018 to 2020 timeframe and before, we were largely focused on being a research and development company, trying to advance the state of the art for how the DoD can use information systems to more effectively design and analyze and model microelectronics. And so we're very excited to transition, the secure design capability from the Trusted Stratus to RAMP, and then move on to the next thing. And that next thing was emulation. So
when you say emulation, just to make sure that all listeners are tracking this, digital twinning is kind of one of the root pieces of the emulation process, correct?
That's one of the capabilities that they enable. I'd say it that way, right? Okay. So an emulator is they're made by the EDA vendors, right? So Cadence has one, a family of them. Synopsys has a family of them. Siemens has a family of them. And what they are is special purpose computers. Very large computers, really classified as supercomputers, that allow you to run the chip design, use the design database, and it runs it directly in hardware. So it runs the chip design faster than you would in simulation.
Interesting.
Vastly faster than you would in simulation, to the point where you can actually run software on the chip in emulation. You can manipulate the state of the chip as it's running to inject faults or do debugging or what have you. They're used predominantly in industry to accelerate V&V prior to fabrication. So
verification and validation.
Verification and validation prior to fabrication, so that by the time you get to fab, you have high confidence that the chip will work in the first pass.
Yep, which I believe is a tagline, right? First pass success. I think.
That's right. Yes.
Yeah. So and the beauty of you guys being EDA agnostic, it allows you to work with all of the vendors that provide these kinds of items.
Yeah, we work very closely with all of them.
So you were saying emulation.
So Air Force Research Lab had acquired a number of emulators through various paths and kind of put them in different places at Wright Pat Air Force Base. One of them in the Sensors Director building, one of them in the High Performance Computing Center at Wright Pat, and then a couple at some contractor sites. But they were just kind of sitting there. They were being used somewhat, but they weren't terribly accessible. You really had to be either physically on base or at one of the contractor sites to use them, to actually type on the keyboard on the computer, or you kind of had the sneaker net, right? You called in somebody to go sneaker net themselves over to go type things on the keyboard for you and then kind of mail the results back.
And that's kind of when I started getting engaged, was this sneaker net kind of approach. Hey, I've got government data that I'd like to get put on there. How do I get it to you? And it's like, well, we really have kind of more of a, label and ship kind of approach. So if you get it to us, then we can work it. So interesting. Okay, you're saying.
Yeah, and so we had this crazy idea of maybe we could figure out a way to wire up emulation systems sitting in the High Performance Computing Center to our cloud environment and enable more broad access that way, and do so in a way that still met the DoD's security and compliance requirements. We had done some earlier work just as a very rough proof of concept under the DARPA IDEA and POSH program.
Okay.
There was a Synopsys emulator that was at a vendor site, a contractor site, that we had set up a VPN connection between their site and our cloud. And we did some demonstrations that, yes, this was a possible thing to do. It was highly unreliable. It did work, but it kind of showed the concept that, yes, we could do things in the cloud. We can also connect to an emulator sitting in a data center and have kind of interactions back and forth between them. So starting with that little nugget, we started exploring the idea of, well, could we run a high-speed fiber line between the cloud and Wright-Patt, this data center at Wright-Patt Air Force Base, what's called an AWS Direct Connect. It took about 2.5 years to be able to do that.
Wow.
Because of getting through all the security hurdles and so forth. But we finally were able to. And kind of once that happened, and once we got the accreditations in place for the emulation systems on base and for the cloud piece, so it was all properly operating under ATO at this point at IL4, impact level 4, so it could process controlled unclassified information, or CUI. That's kind of when the spigot started opening up, right?
Yeah.
We got a few. We were working with AFRL sensors to find some pilot activities to kind of start getting some experience working with emulation and start showing what was capable and possible. And those all were highly successful.
Well, and being able to communicate at the CUI level, now the government has the ability to, have more of an open dialogue, right? And before then, there's a lot of limitations. So they can, trickle in some information, but the real meat of the discussion has to happen in the CUI level or beyond, right?
Or beyond, that's right. Yep. And there were, we had those pilots were from across the defense community. So there's some DARPA pilots, there's some program pilots, there's some research pilots, and from a mix of defense industrial base and government.
So small types of
very small,
like seedling kind of
things, yeah. Right.
And
again, remember the idea of using emulation within the DoD at this point was still brand new.
Yep.
Right.
Yep.
I think these were some of the first emulators acquired, right? And these are some of the first uses of those emulators.
Yeah, and as GOMAC typically goes, I was talking with a number of the EDA vendors. Cadence was the last discussion that I had, and they were talking about the years it took for people to adopt on the defense side to adopt the idea of the use of emulators. So now with all of these seedling pieces, this sets up the framework for what I believe is the next big milestone that you guys have achieved. Maybe you want to talk about that a little bit.
Yeah, so we're really excited to be working with the F-35 program on Remedy. I have to forgive me, I can't remember exactly what Remedy stands for.
It's alphabet soup in the government.
It's one of the alphabet soup things, yes, off the top of my head. But it's an activity where we're providing the computing infrastructure to implement a digital twin of the microelectronics on the platform to allow them to do the verification and analysis they need to do to be successful for the kind of next technology refresh.
And this is huge because as an outsider looking in, once again, a lot of challenges associated with coordinating not only with a program, but this is a joint service program, right? So it has a JPO. So now you've got multiple different voices coming in from different services that have to align with a defense prime. Then it has to align with a cloud capability that is built on the foundation of seedlings. And then you have this other piece, which is emulators that are spread out across, not really being used as much. So there is variables across the board. And lo and behold, now you've been able to not only iron out a lot of these, kinks and concerns, but provide a capability for the government that is extremely unique. And tell me if I get this wrong. There's really three major pillars for microelectronics in the defense space. You have your security aspect. So things like the trust program and the such are all built on that foundation. You have acquisition. How am I going to buy the components and where am I going to buy them? And then the sustainment piece. How am I going to ensure that the life cycle of these systems is going to maintain its overall operational timeline? And typically the electronics fit into one, maybe two of those bins, but they're not really set up with the way that government contracting is, acquisition timelines, et cetera, to encompass all three. Now you're putting together a framework that not only allows for all three to be addressed, it buys down program risk, program timelines, program costs. I mean, it is just a complete paradigm shift.
Right, and it does so because it's pulling all of that kind of post-fabrication work, or at least a good chunk of the post-fabrication testing and evaluation work, to before fabrication. So, which is, fabrication is kind of the critical point, right? That's when things get real and very expensive. If you get something wrong in the chip that's fabricated, it's a 6 month to a year timeline before you can do another run.
If they don't cancel
If they don't
run,
cancel, that's right. So there's a lot of risk that comes kind of post-fabrication as you're going through test and evaluation. And so being able to pull that pull that into the digital twin realm to be able to do that analysis before you go to fab yields really high ROIs, right? Significant ROIs that we're seeing. And so, programs that have used trusted as some of these early pilots we're seeing 20, 30x ROI.
Wow.
And it comes from exactly this. It comes from not needing, finding problems before it goes to fab, right? Finding problem, not having to rip out components, in an airframe. Being able to replace just a single chip kind of thing instead of having to rip out all the cabling in order to meet your performance requirements. Things of that nature, right? Being able to do that level of analysis that isn't really possible without having a system like an emulator to run the chip in a way that you can analyze it. And again, doesn't run real time, doesn't run right at real speed, but it runs fast enough that you can actually implement these things and start to really have a concept of the digital twin of a microelectronic component.
Well, and the magnitude of this is just astronomical because many in our industry, reflect back to the COVID days, right? And there was a lot of different systems that required, 30-cent components for, different kinds of commercial applications, washing machines, Ford F-150s. I mean, it is a spectrum of items that were just not commercially available. If we have a Defense Department that is able to have an operational capability because the lack of a component being able to be fabricated in a timely manner. Imagine having to, fight a battle where you don't have F-15s, where you don't have Abrams tanks. I mean, that is a huge crippling factor for the United States. So now you've created a set of solutions that is an enabling function for that sustainment architecture, which is really exciting, and it's gotten a lot of attention, not only from the JPO and the F-35 program. It was quite a bit of discussion, as you and I have talked about, with the ME Commons program at this conference. It's gotten a lot of interest in discussions that we just had with NASA and JPL with some of their investments. How do those things, foundationally, being very specific with the HPSC, the high performance space computer, a foundational technology that is supposed to have legs and grab into all of these different new programs. Emulation is a way to go ahead and capture this, and storing it in a Nimbus-like solution provides that opportunity for leverage, buying down risks, cost, et cetera. So,
we see this as a not just a cross-service capability, but really a capability that enables the government and industry, again, to be able to do this digital twin modeling of microelectronics to realize those benefits.
So now you've got a foundation, right? You've got this foundation of yet the next pillar of, wins, I'd call them, as the F-35 program. So what's next for Nimbus? As you're seeing the horizon of, all of the attention that the United States is putting, chips, whether or not it's going to be modified under the current administration, keep the course. You have things like the TNAM program, about $1 billion annually of government funding in microelectronics, maintaining the service labs, and their investments, and then the adoption that is coming in from some of the other ARPAs, ARPA-H, ARPA-I, realizing microelectronics is a foundational technology. It seems like the paradigm shift in the government is now is saying, look, microelectronics enables things. You cannot have hypersonics without microelectronics, but you can have microelectronics without hypersonics. So that's kind of the environment we're in today. So where do you see the future of Nimbus?
I think, I've heard the F-35 referred to as a flying computer or a flying network computer, right? It's really, there are a lot of components in it that used to be hardware that are implemented in software now. And, that comes with the ability to, change the capabilities of the platform kind of anytime you want, right? Which is a unique and important need for the DoD in the modern world, right? The modern battle space. And I think that is the direction that most of the other platforms will be heading. I don't have specific knowledge, mind you, but one would assume that the benefits of having a more software-driven capabilities on a platform within the DoD, within our weapon systems, right, is a massive benefit over our adversaries, and it's going to be the direction that the DoD continues to head in the future. So, I see there are a lot of opportunities for this digital twin capability, right? Just similar to what we're doing with the F-35 program, to do the same sorts of things with other programs going forward in the future. There are also areas, that on kind of more legacy platforms, that I think there are important applications. There's obsolescence questions, right? So there are plenty of old microelectronic systems sitting out there, subsystems sitting out there in these legacy platforms. They're still, flying, floating, right, orbiting, and they need replacement parts that don't exist. They're not manufactured, right? So the question is, how can you create a replacement part for something that is obsolete and not manufactured anymore, and something that ends up being bug for bug compatible with the software that was running on the old electronic system, so that you don't have to go back and re-qualify that software.
It's interesting because we've mentioned the Air Force a number of times here, right? AFRL specifically, which lies under AFMC, right? I can just only assume that the communications from an AFMC perspective that are heavily influencing sustainment naturally will dovetail into the Air Force Sustainment Center. And now they have an opportunity to say, look, I have an ability to be successful in my mission, be able to sustain my weapon systems by leveraging a capability that, God, 10 years ago was not here, 15 years ago was not here. Those same systems that were operational today that were 10 years ago, or the ones that were in design, now can go back in and get emulated and have an ability to make that tail of sustainment last a lot longer than one originally perceived is exciting. And in doing so, and now I'm kind of thinking in my own wild brain here, one could assume that there's just now emulation capabilities populated all across the United States. Wherever there is a system capability that is needed, a sustainment funded activity or some kind of sustainment ecosystem now is going to be synonymous with emulation, and the interconnectivity would come from a Nimbus Services type of approach.
Yeah, that's a large part of what our vision looks like. That's right. And how do we interconnect all those pieces together so that you don't just have an isolated sustainment set of digital twin capability for microelectronics, but that's integrated into Air Force Research Lab set and Naval Surface Warfare Center Crane set and the Navy set and the Army's set and so forth, scattered out all around the country, because they all have there's commonality amongst the microelectronics and semiconductor technologies they use, and there's certainly ways to gain economies of scale, to learn from what other programs have done, and to be able to aggregate that all together so that everyone can benefit from it. Again, within security and compliance requirements, right?
Yeah,
ensuring that nothing's shared that's not supposed to be.
Outside of just the Nimbus go forward question, where do you see defense microelectronics going in the future? And how do you see, the stuff that Nimbus is playing a role in helping to accelerate some of those things or change the direction?
Yeah, my experience in microelectronics is entirely within Nimbus. So I'm looking at it from the lens of the computational systems, the data systems, the networks, the digital twins, right, that enable these kind of capabilities more so than the actual semiconductor technologies themselves. I'm not the person to ask about what feature size is going to be the next great thing. Absolutely. Or what the right semiconductor material is to achieve some performance specification. But from the general trends I've seen over the last few years, right, it continues to push toward more advanced nodes, or I should say pieces of chips moving toward more advanced nodes, other pieces of chips perhaps staying at more state-of-the-practice or legacy nodes, depending upon what's best, and then integrating them through chiplets and through heterogeneous integration, or kind of whatever the correct term for it is these days, in order to effectively take what was a full board or full LRU and put it into a single chip. And so that brings up a lot of intriguing problems that we haven't had before. For example, just kind of basic concern, you have a chiplet sitting on top of another chiplet with some substrate between them. how do you know how hot it's getting in the middle of all that?
Yeah, and the computation piece, I think, is the exciting one, because as people progress in the high mix of technologies, whether it be digital logic and the shrinking of node sizes, 3 nanometers, 2 nanometers, et cetera, whether it be power electronics, silicon carbide, gallium nitride, whether it be analog mixed signal, there's such an array of electronics and now it starts to become highly critical material stacks, density problems, and the such. And you don't have the luxury of doing multiple, like you said, tape outs of electronic components. So where does it get all rooted back to? Heavy computational analysis and in the ability to buy down your risk so it's one time, single pass success, right? Like that's what you're going to be able to do, will ensure that the electronics community continues to drive in a particular direction without spending unnecessary time and dollars to go in and explore areas that one may not have commercially available today. New materials, diamond substrates, for example, black phosphorus. All these different types of pieces are great concepts that without the computational capability, the opportunity or the probability of success drastically goes down if you don't incorporate it.
Right, and the real question and the real driver becomes, how do you enable first pass mission success, right?
Absolutely.
How do you understand what the mission needs are, the mission requirements are, tie those back into the digital twin, and be able to have this feedback loop so that you ensure when the chip is fabbed, it works electronically, yes, the logic is all perfect, yes, but also the chip functioning in its environment is able to achieve its mission.
Every operator that will watch this is going to be thankful that you said that, because at the end of the day, it doesn't matter, whether or not it has first pass electronic success. If someone is behind, or in the cockpit of, like I said, an F-15 and their electronics fails, then that is catastrophic from a personal perspective, a national security perspective. The problem space just continues to grow. So
absolutely. We're all here to support the warfighter.
absolutely. So Schoeller, this was great. I really appreciate your time here. And I'm looking forward to continuing to track how Nimbus Services not only influences the electronic community, continues to support the warfighter, but also makes such big impact. So I have no doubt that next year's GOMAC is going to be full of exciting new, not only opportunities for you guys, but successes that we can look back on. So
Well, thank you. I hope so. And this has been wonderful. Thank you for inviting me.
Absolutely.